everyone. I am Mr. Peterson. I'm from Team 2220 Blue Twilight. I am a automation engineer, and I've been working for almost 20 years with 3D printing.
I am Max Hansen. I am one of the team captains for Team 2220. This is my 4th year in FRC, and I think 9th year in FIRST overall. I recently just got a 3D printer and have absolutely fallen in love with the technology and how it all works out.
So what we're going to talk about today is that while 3D printing is a disruptive technology, it has a lot of unique characteristics and there's limitations. You have to understand and respect them to produce the best parts. In this session, we're going to discuss 3D printing. We're going to start from CAD, slicing, print orientation, things like that, so that you can make better choices when you're making your own parts. One thing you do have to remember, though, is all filaments, materials are going to all be a little bit different. Your machines are going to be a little bit different. The slicers that you use are going to be a little bit different. So the important thing is to understand the technology of how they work so that you can find all the right settings on your equipment and make it work for you. Now we're going to focus on FDM, fused deposition modeling. There's many other types of 3D printing, but this particular one is very useful to robotics students because the equipment itself is inexpensive. It's small. We can fit in a lot of desktops and corners and things like that. It's fairly mature as the new technology goes. And you have a lot of choices. A lot of the slicers and a lot of the equipment that are open source so that you can hack them if you want to. You can get a lot of different nozzles and hot ends. You can use rigid plastics. You can use elastomers and things like that. It's very, very flexible and it's very, very capable. It's also quite simple, as you can see from this drawing, for those of you who aren't that used to how the innards work on it. It's just roll a filament that goes between a pinch roller driven by a motor, heated up through a filament, and it's deposited by an XY table. Now this seems real simple, and it is, but the quality of how it's implemented and a lot of other things in it are what add up to making a good part. I think the phrase is, the devil is in the details. So let's look at FDM technology close up.
So with a look at this FDM technology, you can see kind of how each layer of printing is laid out. And it's kind of like if you stack toothpicks or pasta or something. And you can see on the left picture here, this areas of overlap isn't very large, and there's a lot of big gaps between the print. This is not what we want when we do 3D printing, and we're going to talk about some of the things you can do to make it look more like the image on the right, where you have this overlap between the parts that help bond each individual strand together and make the part much stronger overall.
One thing I might add to what Max has said is, as you can see, there's going to be some voids in there no matter how well you do this. And so what that means is that a 3D printed part like this with FDM technology is never going to be as strong as an injected molded part. So if you're trying to replace a part like that, just remember that you may have to make it a little bit stronger when you make a 3D printed part.
Yep. So then another very important thing about 3D printed parts is they are anisotropic, which means that a physical property that they have is different when measured in different directions. So when you come to 3D printed parts, it's due to strength and where you pull on it. So if you pull on a part in the Z direction where the planes are on top of each other, it's going to be much easier to pull these pull the 3D printed part apart than it is if you pull it in the X and Y direction, because in the X and Y direction you're actually ripping apart the strands, whereas in the Z direction you're pulling apart the planes where they were melded together, which is not nearly as strong of a bond. So that's something to keep in mind when positioning your print and how it lays on the print bed.
Then I want to get into some CAD related issues, Max.
So one of the biggest mistakes that I and many starter 3D printers make is that they use sharp corners. This is one of the biggest things that you can do that is wrong. You want to add a fillet into that sharp corner to relieve some of this stress. As you can see in the bottom left, these abrupt changes cause these stress lines to crowd in these very high stress concentration areas. And then in those areas, the part is prone to breaking and snapping. So then if you add a fillet or fillet, you're able to smooth out those curves, and it's much less crowded in those areas, leading to an overall stronger part. This is a fairly small change when it comes to the big picture, but it makes a huge difference when looking at the overall strength of the part. And then this bottom right image here is actually a stress tester on the computer. So you can put in where you anchor the part and where the force goes. And as you can see, these sharp corners here are highlighted in red because they are very, very prone to breaking and are one of the highest stress areas on any part you can make. So then another look at fillets. In the top, we have a poor design here that has these sharp corners. And on the right side, we have a good design. And on average, your fillet, you want to have a 0.5 the thickness. So if the thickness of your part is a quarter of an inch, you usually want to have an 1/8 inch fillet as your smallest possible. Again, on the bottom, you can see the left side is a very poor design, no fillets. Those hands are going to break off very, very easily. And on the right side, you can see the inner fillet is smaller than the outer fillet. So the arms are going to have much more strength when pushed outward than they are when pushed inward, but that's okay because the part was most likely designed for that. But even including those small fillets makes a big difference. And then we can look at FEA, which is finite element analysis. In robotics, we may not get to work with this as much, but especially in industry, you will. You can take a 3D printed part and add in, like I said, where the part is mounted against the wall or the parts of your robot or anything else. And then you also place in the force vectors of where the force is going to go. And then as you can see, the computer does all of it for you. It runs all of the calculations, and it can tell you where the part will feel the most stress and where it's most prone to breaking with this red. So you can see here, that's one of the force, where the force is going. And you can see on this top part, the red is right in kind of in the middle of that stick out. So that's where the area takes more force. And then you can know that, so you can add a little bit more strength there. And then on the left or right here, we see gear tooth basically. And you can see that when the force is applied upward, that's where the gear tooth gets the most stress. And then you can maybe increase that fillet a little bit to make it even stronger. So you can see as he's circling, those are the areas of highest stress that are most prone to breakage and snappage.
This is a interesting technology, and it basically uses the model that you've made and does some more calculations and uses false color, sort of like meteorology does, to show you where the higher stresses are. So you can go back and change your design. If you have enough information about the forces and everything, you can actually create a much better part before you even built the first one.
Mm-hmm. And then as you can see here, this is a part. The part, I'm guessing, was first designed with just this L bracket, which would be strong enough on its own. But then I'm guessing the team had to add this sort of screw hole thing where you could screw in a screw, and they realized this might not be as strong. So they added, you can see one support structure here, another here and here, and then yet another one here to sort of help this L bracket stay strong. So this is the kind of things you want to be looking at with parts. You want to be able to predict where it could break and where there could be problems, so that you can go in and fix these problems before they come up. So this is a fairly well designed part that should not be able to be broken easily if put under high levels of stress.
It's also a nice part then in that if it's printed this way, it doesn't need any supports either.
That's another thing to keep in mind while printing, is where supports go and how many you will need.
Okay, so let's take a look at some appearance factors, in this case related to nozzle or layer height size. Everyone's that's had a 3D printer has made little models and things like this, and they can tell what the layers look like. And in a case like this, if you want a better looking print, like the one on the right side, you could use a smaller nozzle and smaller layer heights, and it ends up looking better. You don't always see the build layers on there, and that's important for a layer or for an appearance part. But in FRC Robotics, one of the things we're building is a functional part. You want it to be strong, and of course as lightweight as possible. Appearance isn't one of the things that's that important. You may choose a color or something maybe that matches your team to make it look a little better that way. But as far as what the layer heights look like, that it's not something necessarily to be concerned about. We're going to be talking about issues related to functionality, and that's what's important on a robot part. There are some issues here, as you can see, that in appearance that are related to layer height. You can kind of see that this one has really thick layers. It's really coarse, and this isn't a flat surface. This is sort of a slope surface. So this is how it makes that part. This one up here on the top, that one was made with medium size layers and things like that. The layers are a little bit less apparent. And then the one on the lower right, that one was made with fine layers, and it looks fairly smooth for a tapered surface. Again, if that's important to you, that's what you'll do. You'll use smaller nozzles and layer heights. It'll take you a lot more to make. It'll look better, but you have to decide if that's important to you on your robot part, because it probably isn't going to add to any of the functionality. This right here is another example of some parts that are made with different layer heights. And the thing about layer heights is it takes a lot longer. This is the same part. You can see it's taken 30 minutes for this part on the left, 18 minutes for the one in the center, and 9 minutes for the one on the right, with the different layer heights. And quality is a little better in appearance and everything like that. I think the one on the right could have been made a little bit better, but time is important. You bought a 3D printer because you wanted it to make prototypes for you very quickly. But then you went ahead and you made your layers so small that it took forever to do it, sometimes overnight. And then there's issues with it possibly failing. So therefore, again, you have to consider that what you're really looking at is functionality. And if you take this to an extreme, you can see right here, this is the same part. This one has a standard 0.4 millimeter nozzle that just about everyone has. This other one has a much larger. This is actually a quite large 1 millimeter one. But look at the difference in time. 11 hours, a little over 11 hours, and not quite 2 hours for the same part. And they may be functionally work the same, but you could have made several other ones in the same amount of time that you took to make the first one. Maybe this first one's an appearance part, and that's important, but that amount of time you may not have. And as I said, sometimes for long prints like that, a lot of machines will fail if they're over just a couple hours. So that's a dangerous thing, and it happens probably overnight when you're not watching it, and then you have to start all over again.
So we can move on to some other major FDM printing choices that affect our print time, failure resistance, and most importantly, the strength of the part we're making. The first one is infill. On most machines and most slicers, your standard infill is going to be somewhere around 25%. It might be 20, it might be 30, but that's your standard. And then you also have all the way down to 0% infill where it's just the shells, and all the way up to 100% infill. And you want to be really cautious with infill because you may think as it goes up in percentage, the part gets stronger, but that's not always true. And 100% infill is very, very rarely the way you want to go. You usually want to stick to around 20% or 30%, depending on the part you're creating.
And again, this 100% is going to take a lot more plastic, and it's going to take a lot longer to make this part. And it may not even be necessary.
Yes.
I mean, this one,
it will be much, much heavier as well.
Right. Think of the analogy between tube and a solid. In robotics, people tend to use 1-inch square tubing. It has fairly thin walls, doesn't it? But it's very strong. And you wouldn't be likely to use a solid 1-inch bar because that would be extremely heavy, even on aluminum.
It's just unpractical. And then one of the most important things when it comes to printing is shells. Normally your default shells is 2 or 4, and in the chat quick you can type if you ever have changed the shells or not. If you take away one thing from this presentation, shells is probably the most important thing. The number of shells is directly related to the strength of your part, and if you do increase these shells, it will almost always increase the strength of your part here. And as you can see in the top picture, these gears, they only have 1 or 2 shells. See, maybe there's 1, maybe there's 2. And then that really negatively affects the strength of these teeth, and it makes it much harder for this gear to go on for a longer lifespan without breaking.
You can see on the right too, there's the 2 yellow parts. The one on the left has about 2 shells, the other one has about 6. And that hole in there is either for a bolt pass through or it may be threaded. And threading is going to cut some of the interior part of that out. So you need to make it bigger to start with. And if you put a bolt on there that's holding it in compression, you need a much bigger solid piece there so that it doesn't crush the part. Otherwise, it's just like the one on the left, it's just compressing the infill, and that's not nearly as strong as a solid ring around there. Same goes for the exterior parts. And one of the important things about infill on these gears is this one has a splined shaft on it, and that internal part has to transmit out to the gears. So if you don't have a very stout infill on there, it won't be able to transfer the energy. It'll probably just strip immediately.
So then we can talk about printing infill on these critical sections of the robot that maybe are a little bit thinner, but you need this part to stay alive and not break. So there's 2 ways to do this. One, you can do it with shells, as you can see in this cross section 1, and the other is with infill, and that is with cross section 2. As you can see here, your cross section 2 or your version A is going to be very poor because when you push the force in this way, it's just going to snap right off right down here. You can ignore the fact that it doesn't have fillets. That would also help. But this part is just going to snap off nearly immediately whenever any force is put upon it, because this infill is not nearly as strong as having these shells. So if you are able, you can edit the number of shells and actually force the machine to go in and print just this section of your piece as solid or as solid as possible. And that will greatly increase the overall strength of your part and make it much less likely to break when force is put on it, which for critical sections of the robot is very critical.
On a part like this one on the left, you can see how they, as much as possible, they got rid of the infill on here, on cross section 1. And there's still a little void up near the top. Sometimes that can't be helped. The machine only has a certain width to it. But if you create the best of it, the rest of it with a lot of shells, and you adjust it accordingly, you'll come pretty close to filling this in completely.
Which in this situation is what you want to make your part stronger. here. Oh, Mr. Peterson, you stopped screen sharing.
Oops. Hold on a second.
Okay, awesome. So then you can see here, this is another example of printing with this infill on these critical sections of the robot. On the left, you can see this is going to be a very breakable and poor part, especially on this top portion. It's nearly completely hollow, so that segment will break off almost immediately. And even on the bottom here, it's hardly connected to the main part, so the strength there is abysmal. But on the right here, you can see that our user has altered maybe the geometry a little bit and the print settings so that it's infilled or using shells on this section, as well as this bottom section to keep the part much stronger.
These are the kind of things that you set up in your slicer.
Mm-hmm.
And if you're not sure what's going on, for instance, professional slicers, you can step through the layers and you can see it. And that's something that you might want to check out in your own, because most of them do have it. You can step through each layer and see how it's made them and check it out in advance.
And
Another
you can check
thing
your
is,
sorry.
Yes, go ahead, Mike.
You can check your most critical layers for errors, and then you can go in and edit that error so that it doesn't become a problem.
Another way you can check it out is in 3D printing. They always say, always check the first couple of layers. The first one to make sure it's bonded properly to the build plate, and the ones after that to make sure that they're bonding to each other. But you can also, once it's printed the bottom layers and it's getting into the sidewalls and everything like that, you can check just to make sure it's doing things like this properly.
So then this is another example of this infill. So as you can see on the left here, this inner shaft has very little connection with the outer square edges. So this inner shaft is going to strip out nearly immediately, even with any infill on the inside. So you need to be editing your layer height or your width so that this connection is much stronger and your part is less likely to break. And then you can see here, this is about the perfect thing you can get on this top gear. There's no holes. This is looks like a fairly strong part, and it should be able to last a while. Whereas the bottom one with lots of these infill gaps is most likely going to strip out or break these teeth off fairly quickly.
Yeah, that perfect one's really hard to obtain.
Mm-hmm.
And the one that says some infill, that's
gonna
pretty
be
good.
unusual. Yeah.
Yeah, that's probably what you're going to end up with. So let's look at some mechanical strength and failure factors here for 3D printing. Now, the first thing you want to think about when you're designing a part is what kind of load it's going to impact. Here we show the three important ones that you're going to encounter. First one is your static load. Most everybody knows how to calculate that. You know, if you want to lift 100 pounds, you know what size part you can use based on its tensile strength. But another important one that FRC robots encounter is impact strength. It's usually a very high rate force on it. As you can see, it goes up very quickly and then back down, but it's usually a lot more than static. And that's, for instance, if you run your robot into a wall, it comes to a stop very quickly, and the forces on it, that's actually an impact. These are all related forces, but they're a little bit different, and you need to know what you're going into, because that may determine how much of a safety factor you're going to add, how much larger you're going to make it, because you don't want to, for instance, say, I'm going to make it big enough to support a 100-pound load if I'm going to pick up 100 pounds, because there might be some deficiencies. You might have made some errors. There's some problems with a little bit of problems with the printing, or there might be something wrong with the filament that you bought. So you might decide you're going to do at least make a part for to carry a 200-pound load, just to be sure. And if it's a little bit overbuilt, it's also more likely to handle an impact load better. So how do we measure these things? Well, we use something called a tensile tester. I use these in industry. At 3M, we have loads of these around. They're quite expensive. You know, they're maybe 250,000 a piece. They look complicated, but they're fairly simple. As you can see on the right, they're just two grippers for what you're testing. There's a load cell to see how much force is on it. And then there's a bar that goes up and down and applies the force to it. So let's see how one of those works then. You should be seeing the video now. There's no sound to it. There you can see the machine. Got the two clamps and the sample in between. Once you set it up, you just start it and it does everything for you. It's kind of nice. And it makes this graph. It has all the information on there. You can see the part necking down, and it breaks. These are called dog bone samples. They kind of look like a dog bone. Sometimes they're round on the end, but you can see what. Okay, back to this. What this machine creates is a stress strain curve. If you're going to become a mechanical engineer like Max, you're going to encounter this, because this is a very important part of mechanical engineering and material science. As you saw from the video, the machine creates this red curve, as you can see here. And there's a section here that's linear. Right here. In that section, it has what's called elastic deformation. What that means is if you pull on it in this section and you let go, it'll return to its original state. But if you keep pulling on it, you can see how it starts to go a little non-linear. And in that section, it's permanently deformed. If you let go of it here, it'll be a little bit longer. There'll be cracks in there and things like that. And you get to this point, and then it finally breaks. So if you're looking at a stress strain curve, just remember, this is a section you want to be working in. On the stress strain curve, stress is in the y-axis, strain is in the x-axis. And stress is the machine, for instance, pulling on the sample. It's the amount of force per unit area that you pull on it. You keep pulling and the force increases, and what that does is it causes the sample to elongate. Strain, it makes it longer. So, and strain is the change in length over the beginning length. Again, it shows this gold triangular area. That's the elastic region. That's where you want to work. Here's a stress strain curve of various materials that you might actually end up using. For instance, a brittle plastic. Although even carbon fiber tends to break this way. It's very, very stiff and then it fails catastrophically. But some old or poor plastic could be this way too. These tough and strong plastics, that kind of material is something like a polycarbonate. Tough describes a material that can absorb a lot of energy. And for instance, a bulletproof window that absorbs the energy of the bullet without breaking. So this is a very tough material as opposed to a brittle material which couldn't absorb it. Glass is a brittle material. If you hit the glass with the bullet, it would instantly break. And if we go down here, you look at an elastomer. Elastomer is another type of polymer, but it's one that can elongate. Classic elastomer is a rubber band. You can see how if you put a little bit of stress on it, it elongates just forever. And its breakage would be way off the scale because that's what it's designed to do. And you have an opportunity in 3D printing to use some of these materials. There are some stretchy materials out there that you can buy and run through your 3D printer. Some of them are more capable than others. Ninja Flex was one of the early ones. And it's a very interesting thing because if you make a part, you can change how flexible, how stretchy it is by changing the infill and the external shells. That makes a difference that isn't as apparent with a solid plastic part. Now here we have some common materials in the material specifications for filament that you would be likely to use. ABS, nylon, PLA, it's very common. Polycarbonate, that's one that's available. PEI, otherwise known as PEEK. That's probably not one you're going to use because you can see it's very strong. You look under tensile strength, it's the strongest one there. And it also has a very high deflection temperature, which could be very important if, for instance, you've got a part that goes around a motor, which of course those get hot. But it's more of a industry one because it's an extremely expensive material. But if we look at some of these other ones, you can see how ones can be stronger than the other. And some of them, for instance, PLA, if you are putting something on a motor, you might decide because its heat deflection temperature is so low that you'd maybe not want to use that one. You might choose some of these other materials. But you can look up, there's these engineering specifications for every filament that you're interested in using. There is a warning here. ABS is a common one used in industry, but in industry, they tend to be used in labs and things like that where the air turns in there are much greater. And the fumes can be more easily exhausted where students tend to use these in a crowded classroom, in a workshop, or even in their own bedroom. And the fumes it puts off can be potentially dangerous. I know even UL has looked into this and they've decided that they too want to give the advice that first robotics students really should not use ABS filament in their parts. They should try to use something else. You may say, well, I've got something that's real fancy, a hood that covers it or something like that. But you may have something like that in your classroom, but you may not have that at home. So just don't use it. There's plenty of other good filaments available.
It's much safer to avoid it altogether.
Right. So anyway, we talked about some of the forces and how to measure them, but getting data for FRC robotics is a little bit difficult. Some of you may be familiar with this guy. His name is Stefan Herman. He's from Germany. He's a mechanical engineer. In fact, he's working on his PhD. He works in the aerospace industry. And the unique thing about him is that he's very curious. As a mechanical engineer, he understands all these forms of testing, stress strain curves and things like that. But he is also a person who does a lot of 3D printing. So he understands how it's made. He understands the challenges and everything like that. So when you combine the two, he does a lot of really good research about these topics and how to make your parts better. and a lot of what we do is based on his work. I encourage you to go out, Google CNC Kitchen, look through some of his videos, and it'll give you a really good idea of how a lot of these variabilities affect the strength of your parts. Now, you saw the Instrand before, and I told you that's about $250,000. And he said he made this for about 100 euros. And he made a video about what goes into this machine. And I've watched that video. I watched all his videos, and it's very clear that he knows what he's doing. It isn't made out of metal. You can see it's made out of big pieces of wood and things like that. But they're very oversized and rigid for what they've done. His electronics, he doesn't have a graphical display. He has to manually input the data and make the graphs and everything like that. But still, he does an excellent job of this. And as I said, he understands 3D printing, which is a unique thing. So it's my opinion that his work is very important and probably about some of the best out there that we're going to get. So let's look a little more into that.
You can see, sorry, with this tensile strength tester that he has made, he's begun to test some 3D printed parts. He designed this hook out of Prusament PLA, the filament he's going to be testing. And as you can see, this is not the same as the dog bone style thing that the industry testers use. And actually, a really important thing about this is it has one force going kind of that direction and then one force going up. So it's testing kind of two strengths at once, per se. And so he can put these hooks into the machine and then begin to test them and see what happens. So then on this drawing, you can really see that when this bottom hook is pulled downwards, it is pulled kind of to the side and up at the same time. So that's where the force is going. And actually, as you can see in some of the testing, almost all of the parts rip right along this line where all of the force is concentrated. And then probably the most important thing to keep in mind when looking at printing, and we'll see through his tests, is the print orientation. So you can print on the z-axis, as in this left-hand picture here, where each layer is on top of the other, and it just prints straight up as your part goes on. And this, as we will see, is fairly bad. And then on the right, you can see we have a printed flat, where it's printed on the XYZ plane, and it's printed from this bottom layer upwards. And that ends up being much stronger. So then here you can see the examples. On the left, we have our standing prints on the x-axis, and on the right, we have our flat printed plane objects on the right side. And as you can see already, these plane lines, you can kind of get an idea that these things will rip much easier along a singular plane than these. And here's the data for the XY hooks. And as you can see, he differed layer height and versus the failure load. So you can see here that actually the 0.1 millimeter tends to be the strongest layer height, at least in this situation. And most importantly, you want to note that the failure load is up in the 70s to 90s range. And then when we look at the Z hooks, can you go back one slide, Mr. Peterson? When you look at the Z hooks here, you can see again that the 0.1 and 0.15 millimeter layer heights tend to be the strongest. But most importantly, if you look over here at the failure load, you can see it's almost half, or in some cases less than half of the other one when it's printed on the XY axis, which is an incredibly drastic change and something to keep in mind. And as well, you can see down here where it gets to the 0.4 and the really thick, this really drops off and becomes a lot less strong and much more prone to breaking. So then here you can see this is our XY printing, where they were printed flat. And you can see when it breaks down here in this bottom image, it literally tore through these print fibers, which is the reason why it was so much stronger. It had to rip through each of these individual fibers in order to break the part, instead of, in the next picture here, you can see here it just tore perfectly along a plane. It just, whatever the weakest plane was in that area, it just ripped the bonds of the plastic straight apart. And then whenever I'm 3D printing and I see a part like that breaks in a flat line or in a perfect plane, you know there's something wrong, because that is almost always a sign of a mistake or a sign of something that can be made better and stronger. So whenever you're
Or
printing, sorry,
or it may be that your temperature is too low on your 3D printer.
yes, so they aren't bonding correctly. So whenever you see a breakage similar to this one, you can think, how can I change this print? How can I change the way it's printed in some way to make this a little bit stronger? And then this, I believe, is an incredibly important graphic. This is putting the two side by side, and you can see this XY in the orange is leaps and bounds ahead of the Z-axis one in terms of strength, and it drops off less as you get thicker layer height. So this is pretty much the most important thing one of the most important things you want to focus on when printing. You need to think about which axis you're printing on and which axis the force is coming from.
A good analogy here is wood. If
Hmm.
you have a 2x4 cantilever 2x4, it's quite strong because you would have to break it along the axis of the fibers. Where if it was built up with end grain, it usually breaks fairly easily, because just like the bond between the filament layers, the bond between the cells isn't that good in that dimension. Let's talk about some infill geometry. There's a variety of types you can have here. You'll have to check into what yours does as a default, but you can change it. You can change the geometry and you can change the infill. And that'll change, for one thing, your print time. You can see how some of the honeycomb ones and like that are going to be a little bit longer. This is going to vary by machine and by slicer, but in general, you can see how the grid type ones don't take nearly as long. And when this was examined, I found out that, for instance, from the left slide of weight, you can see that the triangular one actually weighs more. These are all supposed to be 35% infill, but analysis showed this was about 45%. So again, these things can vary a little bit. But the important thing is the weighted one, the weighted strength here, that takes that into account. And you can see that the honeycomb ones tend to be a little bit stronger. It's not dramatic, and you'll have to decide if the extra time is worth it. But that particular factor or test shows you what difference in geometry makes there. This one just summarizes the whole thing. You can see here, you've got time, strength, and weight. So if you look at this graph, you can say, well, if weight's important to me, I'm not going to use triangular ones. And but if strength is important, maybe I will, because that ended up being one of the stronger ones. And of course, time to print, they're fairly close, but you're going to have to decide for yourself which one of those works is most appropriate for the part that you're working on. And then infill depth.
Yeah, then we can look at some infill density, which is the percentage of the part that is infill. So as you can see here, he just ended up looking at a full honeycomb pattern and a rectilinear pattern. And as you can see, as they go up, much to how you would expect, as the infill percentage goes up, so does the strength. But it's important to see that down here at like the 20 to 40 range, the honeycomb is actually stronger than the rectilinear, and then that changes right when you hit about 40%, and the rectilinear ends up being stronger up in that range. So this is print time versus strength. So you can see, again, as rectilinear, as the time here increases, it gets so much more stronger than the full honeycomb pattern. So if you're going for this 80 or 90% infill range, rectilinear might be the way to go. And it's just another thing to consider when choosing what to do with your part, whether that extra time and, more importantly, weight is worth it for the strength that you get.
And he shows grid and rectilinear on there as separate things, but depending on your slicer, it might actually implement them the same way. Mm-hmm. Let's look at some shell thickness and what a difference that makes. So you can see here when he did some testing, he found out, for instance, that if you did 6 perimeters, that ends up being as strong as 6 perimeters is, I think that's 15% infill. It's as strong as 2 perimeters with 100% infill. And you can imagine how much more time and how much more material and how much more weight would be in this one with 2 perimeters and 100% infill. That's a significant finding here. And it kind of makes sense too. I mean, you can see the lines of force here on the left side, the red arrows. They're right along where those fibers are, and it has to break them, whereas in the infill, that's fairly easy to break compared to perimeters. And here we can see one of the things that came out from this testing is that as far as strengths goes, varying the perimeters, increasing perimeters over increasing perimeters makes the part much stronger over increasing density. That's a big takeaway to remember there, is it's in the perimeters. Again, think about a tube. All the strength really is on the outside. Not much is on the inside, so that makes sense. You can see he did a lot of testing, and there's a lot of results here. And you can look through that, and you can kind of see some of the weaker ones have almost complete infill, yet some of the stronger ones have only 15% infill. They just increased the perimeters on them. So even he's tried out obviously a couple of different variables just to see if there's any interaction between them. But it's clear that, again, perimeters are more important than infill. And that goes back to, if you remember, we talked about these two particular parts. One, the gears, where the outer parts, the perimeters, make this gear strong, not only in the teeth, but in the shaft. Although in this particular case, infill is important too, because you need to, as I said, transmit the force from the shaft out to the teeth. And the yellow ones here, they have a lot of perimeters on here as a functional basis, because they want the outer walls to be strong and stiff. And if they want to run a bolt through here, or if they want to tap it, it's important to have a lot of perimeters there too.
Then another factor here is this extrusion width. And then this is a fairly easy topic to understand. Basically, it is the width of your extrusion that's coming out. Usually it ends up being about 100 to 120% of your nozzle diameter. And as you can see in the picture here, it comes out and the nozzle presses down and your string of filament is actually widened a little bit. So here you can see, you can actually edit this setting in many of your slicers. The bottom is Prusa slicer. There's a whole bunch of different things you can change and make this a little bit better. But normally keeping this within the 100 to 120% range works out well for strength. So then on the left, you can see here at this 100% extrusion width, you end up having a lot of these little holes and cracks and crevices like this, where the print didn't quite connect with itself and didn't bond very well. And then, like I said, you end up with a clear cut, which is something you usually want to not have, right? You want to avoid this as much as possible. And this looks a lot like our break from earlier with this Z printed hook. So you want to be thinking of ways that you could fix this. In this way, in this example at least, the way they chose to fix it was by upping the extrusion width to about 200%. And as you can see in this image, the plastic is much better bonded together, and it looks like it looks almost like a molded part. You can see here it just tore straight across the material here, and there's no flat cut. It's jagged, similar to this XY rip here. So you want to try, and whenever your part breaks, you want to be going for this jagged and sort of uneven look when it comes to breakage. And then going back to these hooks, you can see here with 100% extrusion diameter with 2 perimeters is down here. But then when you go up to 200%, it's all the way up here with a similar 2 perimeters. And I think it's very interesting to see this sort of increase when you increase the extrusion. So then some of the conclusions he drew is that using these wider extrusions seems to help this layered adhesion much more, because the layer is squished more onto the previous layer and this bonding is increased. And if you need a strong part quickly, then upping the extrusion width is almost directly proportional to the gain in strength.
So what are the important, from our presentation, what are the important variables that you really want to take away that you think have the greatest impact on the resulting part? Type that in the chat. So let's go into the ones that we think are important here that you should really consider. First one, obviously, is the layer height, or the how it's the print is oriented, because as I said, the 3D printed parts are anisotropic, and this really proved that theory. I mean, it's so much stronger when the force is along the axis of the fibers, because they're in pure tension for them, and they have to tear before they're going to give way, as opposed to in the z-axis, where you have to break the inner layers.
And then the next, probably most important thing, is this infill pattern. And as you can see here, this is just sort of a summary, so you can look at the different variables, what their effects are, and then you can choose the perfect filament or infill pattern for your part.
In the chat, I noticed someone said fillets too, and yep, you're absolutely right.
Yes.
That's even before you build the part, you need to make sure you design it properly with the correct bracing and fillets and things like that. And then I think the third one here is that perimeters are more important than infill. Some of you mentioned that too.
Mm-hmm.
So
if you have any questions,
Yeah,
if you have any questions, feel free to type them in the chat. If you ask, the moderator can also unmute you if you'd like to ask them verbally. I saw we had one question earlier in the presentation that asked, what is our favorite slicer, both free and paid? I have worked with a few, and mine is by far the Prusa slicer. It's just the easiest one I've found to use. It only works with Prusa machines, but it is by far, if you have a Prusa machine, the best one and the easiest to use with the most functionality, for me at least.
Yeah, otherwise, for a free one, I would use Cura.
Mm-hmm. That is another really
that's an open source one that's very actually quite good.
Mm-hmm.
Last thing I want to say is I encourage everyone here to go out and Google 3D kitchen videos and look through them. As I said, I think Stefan is an excellent researcher. He's very methodical, and he has a lot of great results. And because he knows so much about 3D printing and mechanical engineering, he does a really good job creating data that you can use to make your parts better. So with that, we're going to end this presentation. Thank you everyone for coming, and we hope you the best 3D parts that you can make.
I see one question here. What's the favorite thing you 3D printed? And I actually have it on my desk. 1 second, I'll grab it and I can show it. I'm not sure if it will show up on camera or not, but a couple of weeks ago, I was able to print this. It's a cuttlefish and it's articulated. It's not very helpful mechanically or anything, but it's kind of a cool part, and it's cool to see how these joints work together. And it's a fun part to kind of leave on my shelf.
You printed those, did you print the joints separate or together?
And actually, yeah, I was able to print these joints completely together, and then they were movable immediately after they came off the print bed, which is an interesting thing to see, I think.
Yeah, you
So-
couldn't machine a part like that. That's the beauty of 3D printing. It can make things that are essentially impossible. For instance, you can make a ball inside of a closed box. You can't machine that. Not that that's particularly useful, but it does
But-
show you what a great tool 3D printing is.
Yes.
All right.
I think with that, happy printing, everyone. Thank you very much for coming, and we hope you enjoyed. And here's some contact information if you have any other questions.